Hello, here we are for another video. This time I will speak about the gravitational waves, and I entitled my presentation "The Queer Side of the Gravitational Waves," and it will be clear by the end of my presentation why I included the word queer. Okay, so let me start by putting the slide. So just one moment and we start. Okay. So as I said, my presentation today is entitled "The Queer Side of the Gravitational Waves." So my name is Mariam.Cosmology. I'm a researcher at Basque, as you know, and also a lecturer at the University of the Basque Country in Spain. Well, my email is there. Once again, mariam.buhmadi@gmail.com. You can follow me on YouTube, Facebook, Instagram, Twitter, and at Mariam.Cosmology. Okay, I upload all my outreach video to YouTube at Mariam.Cosmology. So what is Einstein's view of the gravitational interaction? So we have already seen how Newton understood gravitation. So essentially when we have two bodies which are massive, the more massive they are, the strongest is the interaction between these two bodies, and the further they are, the weaker is the interaction. Now, Einstein thought that gravity behaved in a different way. So essentially gravity was related to the space-time, and in particular to the curvature of the space-time. So imagine that we have a net like on this picture, and then that net corresponds to the space-time. So essentially the standard space-time is 4-dimensional, time, 1 dimension, 3 dimension associated with the space. Okay, so to make the picture, of course, so we restrict to two-dimensional space-time. So let's imagine that we have this net, okay, and this net is essentially at the beginning flat, but when we put something massive inside of it, of course, the net will bend, okay, the net will curve. And that is what is represented here. So once you have some massive body, then the net is no longer flat, the net will be curved. And that curvature is a measure of the gravitational interaction, okay? Now, the next thing we can ask is what happens when these bodies moves, when we have bodies that moves inside that net. Before answering the question, okay, so we can first of all, look at what happened when we have a yacht, which is going at a very high speed. So as you can see, so behind that yacht or that boat, there are some waves, okay? So when a body is, in this case, we have a yacht, which is accelerating, its speed is growing, then it will leave behind it some gravitation, some waves on the water in this case. So with gravity is essentially the same thing. So let's see what happened with gravity. So what happened with gravity is that when we have massive bodies which goes at a very high speed, and in addition, this speed is increasing, which means that these bodies have a certain acceleration, then they can produce some ripples on the curvature of the space-time, which correspond essentially to gravitational waves. Now, gravity is a very weak interaction. This means that we need very, very, very heavy bodies, and we need very high velocities, okay, to be able to produce some relative large amounts, let's say, of gravitational waves. And for this, we need to look for the heaviest body in the universe, okay? So, and as I said, this is essentially due to the fact that the gravitational interaction is very weak. So the bodies that are expected, and in fact, in some cases have been already measured, the gravitational waves that they produce, are a binary system, which are usually composed of white dwarf, of neutron star, or of black holes. So the prototype case is the one that is shown here. So essentially we have two massive bodies, one orbiting around the other. And because they are very massive, they are spinning they're rotating at a very high speed. So as they rotate, they produce gravitational waves, which are this ripple that we see, okay, over here. Now, white dwarfs are relatively massive bodies, so they have a mass of the order of the sun, okay? But then they have a size much smaller than the sun. They have a size of the order of the Earth, which means essentially that they have a size with a radius roughly of 6,500 kilometers. Now, if we look at neutron stars, so the mass is similar to that of white dwarf, roughly 1 solar mass, okay? But then the size is much smaller. So we go to things that have a radius of the order of 10 kilometers rather than 6,500 kilometers. This means that we are, that they are much more massive than white dwarf, okay? Then the next one are black holes, and those can be extremely, extremely massive, okay? So we know that there is one at the center of our galaxy. There is a body, Sagittarius A star, at the center of our galaxy, which is believed to contain a black hole. That black hole is extremely massive. It has 4 million the solar masses, okay? But then it has a relatively small radius. So light will take only 17 hours to cross it from once, well, not 17 in this case, 34 hours to cross from one extreme to the other one. Or let's say the radius of that mass is concentrated on 17 hours light. What does it mean, 17 hour light? So we know the speed of light, so 17 hours, so essentially 17 times 24 hours times 60 minutes times 60 seconds per minute. And then we will get the radius corresponding to that black hole, which is roughly 120 astronomical units, which means 120 the distance between the Earth and the Sun. Okay, so they are, as I said, we have some kind of categories. So we have white dwarf, then neutron star, even more massive, and then black hole, which can be extremely massive. And the idea at the end is that these we have two massive bodies, a binary system, one is rotating around the other, they merge, and after that they release a burst of energy on the form of gravitational waves. Okay, and this is precisely what was measured back on 2015 in the event GW 150914. So that's the date. So it was the 14th of September 2014 that LIGO and Virgo, and for the first time humankind was able to measure a prediction of the theory of general relativity, which is the production of gravitational waves, in this case through the merge of two black holes. Okay, then they announced the discovery the 11th of February 2016. This was, then they got the Nobel Prize in 2017, and this Nobel Prize was awarded to Rainer Weiss, who got half of the prize, and the other half was between Barry C. Barish and Kip Thorne. Okay. So this was essentially, this discovery was, as I said, the merger of two black holes that release a large amount of gravitational waves. Of course, it's not at all easy to measure these gravitational waves because the gravity is a very weak interaction, and they needed a very precise interferometry to be able to measure these gravitational waves. A couple of years later, in 2017, the event GW170817, again, it refers to the date, so it was the 17th of August, 2017, when this was measured. So in this case, they measure the gravitational waves produced by two neutron stars. And this came with a bonus. So not only they were able to measure the bursts of gravitational waves coming from the merger of these two neutron stars, but they could as well measure through other experiments, aside from LIGO and Virgo, bursts also of energy coming on the forms of waves of the electromagnetic spectrum. So on the one hand, they were able to measure some gamma rays, and on the other hand, they were able to measure electromagnetic waves going from the radio waves to the X-ray waves, okay? So it was possible to measure simultaneously gravitational waves and electromagnetic spectrum coming from the same events, and therefore this was an opportunity to compare the speed at which the gravitational waves travel and the speed of the electromagnetic spectrum, in this case the light, and it was inferred that essentially they move at the same speed. So this was very important also from a theoretical point of view, not only because it was a confirmation of one of the predictions of general relativity, gravitational waves, but it was also a way to constrain modified theory of gravity, okay? Now, why did I entitle my presentation of today, The Queer Side of the Gravitational Waves? As I explained from the beginning, the video that I do, they have a strong component a very strong scientific component, but then from time to time, I also worry about human rights in general. So we did a video for the day of the girl and the woman in science, a video for the 8th of March, okay, to remember the rights of women. And yesterday, the 26th of April, is the day of the visibility, the annual day to celebrate and recognize the visibility of lesbian in society. So scientists, we are not aside from society, we are part of it, okay? And therefore, the extreme diversity and richness that we have on society, we have it also on science and on scientists that do at the end science. So there are scientists like me that belong to the LGBTQA+ community. And one of the most important, there was a very important person involved in the discovery of the gravitational waves, which is a woman who defines herself as queer, and she is also a lesbian. So that's why I named the video of today in memory of the discovery of the gravitational waves, and also, and in particular, because the 26th of April is the annual day to celebrate and recognize and bring the visibility to lesbian in our society. So I thought that this was an excellent example. So gravitational waves are very important discovery on the last year, which involved a woman which is openly gay and she is queer. So then I thought, okay, this is the perfect combination to celebrate the 26th of April in the context of science and cosmology in particular. So who is this important lady? So she's a professor at the MIT. Her name is, Nergis, I put twice her name, Nergis Mavalvala. And as I said, she's a professor at MIT. Okay, she is originally from Lahore, Pakistan. And she say about herself that she's out because she's openly, she say openly that she's gay, she's queer. And she also, she refers that she's a queer person of color, on the sense that her color is a bit more, is a bit darker. And also she said about herself, I don't mind being on the fringe of any social group, because she's many things at the same time. So she's an immigrant on one side, she do physics on a world of man, and on top of it, she is lesbian. Okay, so she belongs to the LGBT community. So it's a lot of things in a single person, in a single woman in this case. She did her PhD under the supervision of Rainer Weiss, who was one of the Nobel laureates in 2017 for the discovery of the gravitational waves. The work she carried during her PhD, as I wrote there, was incorporated in the design of the laser interferometer of gravitational waves, or LIGO, okay, observatory. So of course, she is part of the team that discovered the first signal of gravitational waves. And it is on this sense, on her honor, that I entitled the talk of today, The Queer Side of the Gravitational Waves. As I said, in this video, we combine two things: science, cosmology, in particular astrophysics, on the other hand, human rights, and particularly the visibility of the lesbian on the 26th of April, yesterday. Okay, so let me finish with something Professor Nergis Mavalvala said, and it is the following: anybody should be able to succeed, whether you are a woman, a religious, or you belong to a religious minority, or whether you are a gay. It just doesn't matter. Okay, so this is what she said, Nergis Mavalvala. Okay, so she she's many things in a single person. So shukriya, thank you, Professor Nergis Mavalvala, for being a role model for women doing physics, for immigrants, and of course for lesbian and the LGBTQ+ people in general. Sorry, where there is a star, it should be a plus. Okay, so that's all from my side. I hope you had enjoyed the video. So sciences, this video has two components: one component which is related to science, and another component which is related to human rights. And to the right, we have lesbian to our visibility. Okay, and as I said, that's all, and see you next month on another video. So ciao for now.